Semiconductors and Doping. By the end of this lesson, you should know two methods of improving semiconductor conductivity and also be able to explain what is meant by the process of doping and how it improves conductivity. What is doping? Doping is the process of adding tiny amounts of impurity atoms into a crystal of pure semiconductor material. By tiny amounts, we mean less than one impurity atom per billion. So where we have a lattice of atoms which are all the same type, for every billion one of those, we have one atom which is different. This picture shows a crystal lattice of a semiconductor. What do you notice about it, and what do you think the effects might be? Were you able to spot the difference? If you take a look carefully in the top left, you'll notice there's an atom which is a different color. This atom also has more electrons surrounding it. All of the other atoms within this picture have 4 valence electrons in their outer shell. They covalently bond with all the other atoms in the structure. This gives them 8 electrons surrounding them in total in their outer shell. If you take a look at this one on the top left, this one actually has 5 valence electrons. One of those electrons, because it covalently bonds with the rest of the atoms, it becomes free. So one of those electrons will be loosely bound and able to move freely within the crystal structure. This effectively lowers the resistance of the material. We call this type of semiconductor an N-type semiconductor because it has an extra negative charge carrier within it. Take another careful look at this picture. What stands out in this crystal lattice? What do you think the effects of this might be? This crystal lattice has been doped with an atom which has 3 valence electrons in its outer shell. Now remember, all of the other atoms here all have 4 electrons in its outer valence shell, and all of the atoms will covalently bond. If this impurity atom with only 3 electrons in its outer shell covalently bonds with the rest of them, it will leave what is known as a hole. This forms a p-type semiconductor with holes in the electron structure. Holes can be thought of as positive charge carriers, since electrons from neighboring atoms can move into them and a new hole will be formed in that neighboring atom. In this way, it looks as though the holes are moving in the opposite direction to the electrons. Effectively, you'll have negative charge flowing in one direction and positive charge flowing in another. Let's take a look at how positive and negative charge can flow within a semiconductor. On the right-hand side, we have an atom which is the impurity. This atom has 3 electrons in its valence shell and creates a hole, the positive charge carrier. Next to the green positive charge carrier, we have another atom which has an electron which can move into that hole. Now that the electron has moved into that hole, it now creates a new hole in that neighboring atom. In this way, it looks as though the holes are moving in the opposite direction to the electrons. So where the holes are moving to the left, the electrons are moving to the right. Here's a quick research task. Find out what you can about the types of elements used in semiconductors and doping. Think about what elements are used for N-type semiconductors and what elements are used for P-type semiconductors. Write a short paragraph or list of bullet points. To summarize the learning intentions from the start of the lesson, we now know two methods of improving semiconductor conductivity. We can create what is known as an N-type semiconductor or a P-type semiconductor. We can also explain what is meant by the process of doping and how it improves conductivity. We can take a semiconductor crystal lattice, and for every billion atoms within that crystal lattice, we can put in an impurity atom. This impurity atom could have an outer shell of 3 electrons or an outer shell of 5 electrons, and this will create either a P-type or N-type semiconductor.